Hello everyone, I'm Hongliang Zhang. I'm a PhD student here. Actually, I'm in my 5th year, and I'm a PhD student in applied economics at Oregon State University. And I think I forgot to put my advisor's name here. I should do that. Yeah. My research actually is focusing on assessing climate change impact on weight systems, particularly focus on the East Cascade of Pacific Northwest, because this region is a weight-dominated agriculture system. This first graph demonstrates that the changing climate. We can see that the first bar showed that for the Northwest region, including Washington, Oregon, Idaho, and part of Montana, we can see that in the last half of the century, every decade we have a temperature increase at 0.15, and the rest of the 4 bars show that on the ocean surface temperature actually also increase, but at a relatively lower speed because of the ocean nature. So given this changing climate, my research question is, what are climate change impacts on the U.S. weight systems? There are a lot of debates in this field on the topic, from the sign of this change, whether it is better or worse, or whether, and this is a large effect or small effect. There are tons of literature on this field. Mainly, this literature fall into 2 parts. One is statistical approach, another one is process-based approaches, and economists mostly focus on statistical approaches, and scientists mostly use process-based approaches. And my research kind of fall in 2 parts of this research. And the first part, statistical approach, is from my dissertation, and the process-based approaches is from the project I'm involved in now. It is a regional approach to climate change. So I will talk about these 2 parts. The first one, I use a moment-based statistical approach. So what is a moment-based statistical approach? Let me explain the framework. First, given this weather, I define a climate at a farm is a weather distribution. I think everyone knows that this is similar to a normal distribution of the weather. We have the density, and the current climate at a farm is denoted by this distribution A. And under this current climate, we have a production function for this farm. This production function is a function of weather and other agriculture inputs like fertilizer, irrigation. And facing this changing, this randomness of this weather, the farmer will get an output distribution in terms of either crop yield or revenue, even net return. I will just talk about yield. We can see that we can use higher order moments and mean to capture the distribution of the weather and also the distribution of this output. So it means we can capture the average yield and also the production risk. Now let's look at what if climate change, we get a different weather distribution. We can see that the current climate just shifted to the new climate by increasing the mean. If we take temperature as an example, we can see that mean temperature increases. And also we are going to have a lot of density at the upper tail. So it means we have more extremely hot days. So these high order moments can capture both of these 2 effects. And without any adaptation, we just keep this technology constant, we are going to get a new output distribution. We can see that on average, this mean yield just goes down. But we also can see that the production risk is going up because we have more density on this lower tail. It means the probability to get a crop failure is going up. But farmers are smart. They can adapt to climate by changing some input use, even shift the entire production function by changing land use. we can see that under the new climate, farmers can shift this production frontier and end up at a new output distribution, either by increasing the average yield or reduce the production risk. So this framework demonstrates that we can use the mean and higher order moments to model the climate change impact on the output distributions. And here is one case study result I had. And my study region is East Cascade of Pacific Northwest. And my research here are all just about winter wheat farms. I'm looking at winter wheat yield distribution. And this is a similarly unrelated regression model. And I have all the dependent variables are moments of output distributions, including mean, variance, and central moments and partial moments. By partial moments, lower and upper, I mean lower is the lower till below the mean, and upper partial moments means the upper till above the mean. So, and the independent variables I have include precipitation, growing degree days, and irrigation percentage, and other variables I do not report here. And I want to mention that growing degree day is a measure of temperature. So I just calculate this variable based on the daily average temperature and then sum them up over the winter wheat growing season. And we can see that from the first column, the mean function of yield, we can see both these three, all of three variables are positive. So it means precipitation, temperature, and irrigation have positive effect on winter wheat productivity. Although this GDD is not significant, it's just because of it. For this small region, we won't have enough temperature variation. And look at the 3 and 4, these are variance and the third central moments. For the 4 moments, we can see precipitation and GDP are not doing a good job to explain production risk. But if we move to the partial moments, we can see that actually it implies climate have effect on the shape of the distribution. If we look at this GDD variable, we can see that all the lower moments are not significant, but the higher moments are positive. It means this temperature will extend the upper tail to the left and also keep the low tail constant. So it means this temperature will benefit winter wheat productivity. If you look at the precipitation and the irrigation, we can see that for the lower tail, they both have positive effect, and the upper tail have a negative effect. It means precipitation and irrigation will extend the lower tail to the left, but shrink the upper tail also to the left. So we get a distribution just moving toward to the left. So it means precipitation and irrigation have negative effects on the production in terms of high order moments. So these are major findings from this research. And this is process-based models. And we find similar results if we put we put revenue and cost in the equation. We pretty much the same, magnitude. But if we put net return there, actually the model not significant because the effect on revenue and cost, they just cancel each other. And that is also consistent with the literature we find if we regress the climate or weather variable to their net return, we just find they're not significant. I think the major reason is if we break down net return into 2 parts, they just cancel each other. And this is what I have done for the statistical approach. This is just one statistical approach. Now let's move into another process-based approach. I'm involved in the interdisciplinary project to evaluate climate change impact. And usually process-based approach requires scientists and economists to collaborate with each other. And this framework is in the red box, we can see that climate scientists just generate downscaled climate data from global climate models. So far, we have 14 different global climate models on the 2 greenhouse gas emissions. So in total, we have 28 future climate scenarios. And crop modelers put this data into their crop growth model, like crop system model, to generate the simulated future yield data. And we, based on this simulated yield data, to get the relative yield distributions. I will mention what this distribution look like in a second. And we generate the parameters from these distributions and put into the TOMD model, which is a trade-off analysis model to evaluate the climate change impact. We can get some economic, environment, and social indicators. And these indicators include like what the percentage of farms in this region will lose from climate change, and what is the size of this loss. And this is the framework I used. I will just use these slides to demonstrate how we can use relative yield distributions to evaluate climate change impact on winter wheat productivity. Relative yield is defined as a ratio of crop yields on the future climate over historic climate. If this relative yield is greater than 1, we will see the crop productivity goes up. If it is less than 1, crop productivity will go down. And we can get a whole distribution across farms. And this graph shows that we have 4 different global climate models. We can see that on the different global climate models, we get different average relative yields. So it means on average, the climate change impact will depend on what kind of climate model you choose. So it implies this uncertainty from climate models will bring the uncertainty into economic assessment of climate change. That is one major point. And a second major point is, if you look at each climate model, we get a whole total different distributions. We can see that the relative yield just spreading across farms, either from the maps or from the distributions. So it implies even given a single climate models, we have a huge spatial heterogeneity across farms. Some farms will lose, some farms will benefit. So this demonstrates that, and the major finding from this study is for this region, winter wheat productivity will be likely to benefit from climate change, but we still are going to get a large majority of farms lose from climate change because of this heterogeneity. And also we find the similar results if we bring into the economic model in terms of the percentage of farmers lose from climate change and the size of this net loss. So this is what I have done for the project. And the next step of my research, I'll just compare these 2 approaches to look at how different they are and also assess this climate change impact in terms of dollar amounts. That's what economists care about, right? And to evaluate some potential climate adaptation strategies like conservation tillage or maybe crop insurance. And that's it.